Yep.
Okay.
Looks good.
So, shall I begin?
Yeah.
Okay. So, thank you for the invitation, and forgive me for being a bit out of practice. This is work I did in my master's at UCL 4 years ago, and I've since moved on to somewhat different topics. But it's good to finally get this out there and to discuss. So, this is all about baths and what we mean by an environment and how this is an important concept in all sorts of thermodynamics. So of course, our favorite laws of thermodynamics, they're so useful because they're admitted by all sorts of macroscopic systems. Universality is thermodynamics is perhaps most favorable quality. And we make use of baths not only to define things like temperature and pressure, but also because there's this simple expression which we can use to quantify the entropy of this part of the universe that we're not interested in. And we all know how this works when we go to smaller and smaller systems, which are not so close to equilibrium. We have to redefine entropy in some way. We have to rethink what we mean by it. But we, in some sense, have to rethink baths as well. If we want to represent baths by their microscopic degrees of freedom, we need to make sure that they are very large, they have very many of them, and that they relax very quickly so that we can recover our Clausius expression for the entropy. The archetypical example of such a bath is the Brownian motion, the Langevin equation described mathematically, where we have two timescales. We have our slow velocity autocorrelation of the Brownian motion particle, and we have the immersing fluid, which is microscopic compared to it and relaxes very quickly. And this gives us the Langevin equation. The friction term and the white noise term both come from the fact that the bath is on a completely different timescale, and we can really simplify its effect on the system. Okay, molecular chaos, we know this, but what if we can't separate our timescales? We have to generalize the Langevin equation, and it ultimately comes down to supposing what if the bath's relaxation interferes with the system's relaxation and we can't stratify them? Okay, in other words, what if the environment's response there's some sort of interference on the text there. If the environmental response time compares to the system, that's really what we're asking here. The generalization of the Langevin equation is achieved most simply by inserting two additional things. The first is the memory kernel in the friction term, if we want to express it just in terms of system variables, in this case velocity. And the second one is by making the noise colored rather than white, it has some sort of correlation with itself. Ultimately, we've just added memory to the system. Okay, so how do we perform stochastic thermodynamics on these sorts of trajectories? It's not a simple question. How do we involve time reversal when we have memory of the past, or it's not simple? And what sort of entropy, if we could do it, would this sort of environment generate? Well, there is a rather famous, I think, way of getting around this kind of computationally getting around generating colored noise and also performing these memory kernels, these memory integrals. And that's by the introduction of, you can call it a reaction coordinate, or I call it an auxiliary system. So instead of having the velocity directly subject to the bath's dynamics, we introduce an intermediary, which we call S here, which interacts with the system and interacts with the bath, and its dynamics are influenced by both. In other words, if the auxiliary system is purple, whereas the bath is blue and the system is red, it's dynamically between these two quantities and sort of gives a certain amount of breathing room to the system, which causes the dynamics of the system to have memory. In fact, it perfectly replicates the generalized Langevin equation that I put on the slides before. So what we've done by doing this is to turn a single non-Markovian stochastic differential equation into two coupled Markovian ones. And therefore, the tools of stochastic thermodynamics, including our expression for the entropy production, now automatically apply to the system. So this trick has been used before, but it's worth looking at what exactly happens to the entropy production. The neat thing about this trick is as well is that you can easily tune our coupling constants G and gamma, which measure how closely the auxiliary system is coupled to the system and to the bath, in order to make the system behave in a Markovian way. If we simply set them both to infinity while maintaining this ratio G squared over gamma, in this case, that's just for these particular dynamics, the non-Markovian system reduces perfectly to the Markovian one, which really lets us compare these two different types of environments, ones which have memory and ones which don't. But it's worth some reflection. Does this really count as a non-Markovian environment? Because I've just told you that the equations of motions are Markovian. Well, ultimately, writing it in this reduced form where only the system variables are considered, velocity, no matter how you produce your colored noise and your memory kernels, this is what you're producing. The trajectories follow the same statistics. So no matter how we use, what sort of trick we use to produce our trajectories, they are following this equation. In that sense, we're motivated to call it non-Markovian. And there are differences in the dynamics. So we construct our test system. In this case, it's still a Brownian motion particle, but we add a spring to it just to give it some sort of spatial potential. And likewise, this auxiliary system, S, sits between the velocity and the bath. And we will perform 3 different external protocols, relaxation or performing work on the system to see and solve the Fokker-Planck equations in order to measure the entropy and to see how the non-Markovian system compares to its Markovian equivalent. So our first test case is thermal relaxation. The system is brought into instantaneous contact with the environment, the auxiliary system plus bath, in equilibrium with each other at a different temperature. And heat will flow, and we want to see what sort of statistics this heat flow obeys. So dynamically, the relaxation of the mean square velocity in the Markovian case is a solid line. In the non-Markovian cases, gradually getting more Markovian as the coupling constants are changed by the dotted lines. And intuitively, there is a delay and there is some extra sort of oscillation, extra feedback in the non-Markovian relaxation. We could have anticipated this. Thermodynamically, the entropy production, the mean entropy production, as it evolves towards equilibrium, of course, there's no oscillation because it's the second law, but there is still, as we could have anticipated, a delay in the acquisition of equilibrium. But the mean entropy, as it mathematically must, still approaches the same value because the same amount of heat is ultimately just put into this Markovian bath. Okay, so where might they differ? Well, that could be in the distributions of the entropy production. So here we see a non-equilibrium distribution versus the equilibrium distribution at time t equals 10. The equilibrium distributions are the same, but it goes further than that. Actually, the continuum of distributions which the 2 different environments generate under this protocol are the same, except the non-Markovian one simply visits it later by a delay time. The time delay is the only difference. So every single distribution that you can get from the non-Markovian system has previously been seen by the Markovian one, in the case of thermal relaxation. Now, our second protocol is time-dependent work. We adjust the spring constant linearly over a certain time period, delta t. And here we see the entropy production in these two different values of this delta t. The mean final equilibrium entropy production is different for the Markovian and non-Markovian environments. And furthermore, you can either produce more or less entropy corresponding to the amount of work that you have to do in order to perform this change, depending on the interaction between this delta t, the time period of your work, and the coupling constants of the auxiliary system, which corresponds to the time scale of the non-Markovian environment. So in other words, non-Markovian environments have their own timescales, of course, and that can have important effects for how you do work on the system. And this is this additional timescale is best expressed if we add a driving force, a non-conservative driving force, to the system velocity. In this case, in the steady state, we can see the entropy kind of has this oscillation where it never goes negative in its derivative as a function of frequency. But if we take the entropy production at a given time as a function of frequency for different coupling constants, we can see that the non-Markovian environment at certain values of the coupling constants actually has this peak in the entropy production as a function of frequency, something which the Markovian environment never expresses. And this of course is a form of resonance. It's entirely analogous to classical resonance in the sense that you have 2 different timescales which can compete with each other in ways that will produce additional oscillations, which in this case will correspond to a greater entropy production. Just to wrap up, as the time is approaching 10 minutes, auxiliary systems or reaction coordinates like this make it very easy not only to simulate non-Markovian environments, but also to analyze them analytically. And if you do so, fluctuation theorems, if your system can be recast in this way, your fluctuation theorems and so on, your favorite tools from stochastic thermodynamics, they all automatically apply. It just requires a bit of thinking to make sure that you really are generating the type of environment that you think you are. Intuitively, if you are just relaxing, your distributions will be the same. It's just there is a delay in the non-Markovian case because the auxiliary system just gets in the way. But if you apply external timescales, then actually the interaction between the timescale of the environment and the timescale of your work can have diminutive or augmentative effects on the entropy production. Okay, thank you for listening, and I'm happy to receive any questions.